This is the topic, reshaping convex polyhedra. It's joint with Costin Vilku, who's a researcher at the Math Institute in Bucharest. And he and I have worked together for a while. So, let's see. Okay. So he and I, during the pandemic, wrote a monograph, and we put it on archive, but just recently we revised it. And it's now 250 pages long. It has two parts, and each part is in some sense a single theory. And what I'm going to do is just show you part one and guess the proof of one theorem. And it won't fit into this seminar.
No?
So here's the theorem, and I'll spend a long time making sure everyone understands it. And please interrupt me at any point. So I'll read it. Every convex polyhedron can be reshaped to any other convex polyhedron, Q, via a sequence of vertex excisions or diagon tailings. So I'm now going to explain all the meaning of this. So first, convex polyhedron. Well, this is for this crowd. You know what that is. We don't know how to handle anything that's non-convex. So this is strictly convex polyhedron. And now this condition that Q must be inside P. These are examples. If you had a cube with an icosahedron inside, that P would be the cube, Q would be the icosahedron. It could be kind of reversed in some sense, where you have a many-faceted polyhedron for P and a few facets for Q. And even though we're insisting that Q must fit inside P, if they don't, you could just rescale Q and put it in, and so that it's in some sense universal between any two convex polyhedra. I'm going to use this simple example to illustrate the proof several times. So here P is the cube, and Q is this tetrahedron in the corner. It's very simple, but it's complicated enough that I think you'll get the idea. So let me talk about vertex excision. It is not vertex truncation. So you know what vertex truncation is. You slice off a vertex and you replace it with a facet. That's not what we're doing. Although you'll see this plays a role. So we call them diagon tailorings. And vertex excision and diagon tailoring are just synonyms for the exact same thing. So here's one way to think of these diagon tailorings or vertex excisions. Pinch a vertex between your fingers. Actually, that's an idea that Honolulu came up with. I like that idea. So imagine it's made of paper and you pinch the vertex, then slice it off when it's flattened. And because of that, you'll get two geodesics forming a diagon. And then here's maybe the novel part. Rather than put a new facet on, you suture the cut closed. And Alexandrov's theorem will guarantee that this isn't yet another convex polyhedron. So here's an example of one diagon tailoring. So between X and Y on the regular tetrahedron, those blue edges are geodesics. So that's a diagon surrounding one vertex D. So we cut off there. So D is gone. And now you take the two sides of that diagon and you glue them together, forming this XY. And then apply Alexandrov's theorem, this gluing theorem, which says that is a convex polyhedron. Now, it's not easy for me to see that this goes to this, but it does. So I worked it out. But in general, it's true for any such gluing. And I'll go over Alexandrov's theorem shortly.
Can I interrupt you for a
Yeah,
second?
please interrupt.
So you specify a vertex, But that doesn't automatically tell you what the X and the Y are, right?
Right, yes.
Okay.
So we use that freedom, you'll see. That's used a lot. So here's the outline of what I'm going to talk about. This Diagon tailoring process in some detail. And then just two corollaries and a couple open problems. So the end will be short and the details will take a long time. So here, this already starts to get at what Boris was asking. I'm going to use this example again, but here there are two Diagon tailorings, the red first and then the purple second. And the red one, notice that one end of the Diagon is a vertex, X1. The other end is just a point in the interior of the face, that's Y1. They surround V. So now you imagine cutting that out and gluing the red to the red. And what you've done is you've removed one vertex. You've left that one still a vertex, just sharper. And you added a new vertex here because you've removed some angle. So this is a case where the number of vertices remain the same. Because you remove one and you add one. Now, it's hard to imagine, but after you glue the red together, the shape changes. And I didn't try to compute what the new shape is. But now look at the purple Diagon. It has one end at X2, another end at X3, which is going to be a vertex, and it kind of clips this gluing together. That's what the dashes are supposed to indicate. So this is the type of thing that we're going to be doing quite a bit. And if you take these two Diagons out, you end up with a flat face X1, X2, X3. So that's the type of thing we're going to be doing. We're going to be snipping these in a very particular way, aiming to accomplish certain things, like laying it flat. Okay, here's Alexandrov's theorem, gluing theorem. This is where, when we say suture close, that's what we mean by that. And I assume many of you know this, but I'll just repeat it. If you glue together a number of polygons, think of them as made out of paper, in such a way that you glue them together. I think the gluing comes from the Russian influence. They always call it gluing, but no one ever does use glue. You always use Scotch tape. So you use up all the perimeters, no overlaps, no gaps. The angle at any point is less than or equal to 2 pi. So when you do this, you're putting things together, and you want the surface to be homeomorphic to a sphere. Then, if these three are satisfied, the surface is a convex polyhedron. It's guaranteed. Unfortunately, it's a non-constructive proof, and there is no algorithm to find the polyhedron. You can only use ad hoc methods, which is a serious limitation.
So no known algorithm, or it's proved that you can't do it?
No known algorithm. So there is there's a differential equation whose numerical solution can lead you to the right shape. This is Babenko and Itzmetsia in Berlin. It's very complicated and not something that you could actually use. So I brought this here. I had this idea that if you take a cube, you might be able to snip off all the vertices and keep doing that and make it into a sphere. That was the main idea. And this is the cube with 8 vertices snipped off, and then I glued them together. And you can't really tell, but it's a polyhedron, convex polyhedron of 16 vertices, because when I did the Diagons here, I cut off one and added 2 in all cases. So I added 1 for every corner. So it ends up with 16 vertices. And you just have to believe that this is a polyhedron because it doesn't really look like one. But you can continue to do this. And so, in fact, you could take a cube and whittle it over and over and over again and get as close to a sphere as you want. And you could do the reverse. You could take something very close to a sphere and make it into a cube. So if the two ends of the diagon are in the interior of a face, you're going to add one vertex. You remove one, add two. If one end of the diagon is at a vertex, you keep the number of vertices the same. You remove one, you add one, and the other one is still a vertex. And if both ends are vertices, then you remove one, and the other two were vertices, and they remain vertices, and so you go down by one. So you either go up by one, remain the same, or go down by one, which allows you to go from the cube to 100,000 faces, or the 100,000 faces to the cube. So is the theorem clear? Yes.
So how do you choose the geodesics are the shortest path between the 2 points you pick? So that's once you pick the 2 points, everything is determined.
Yes. So we use the cut locus to find the next point, and you'll see it becomes we don't want to in order to accomplish our goal, we can't just choose any diagram. We have to choose something very specific. And it will turn out that one end is at a vertex and the other end, it has to open just right and not go too far. And there are all these conditions. But yes, we're doing shortest paths around. Okay. Okay, so I'm going to describe the proof like an algorithm, although it's not really an algorithm that much. And so I want you to get the overall idea, and then there are two hard parts to the proof, which I'll have to wave my hands over, but I'll warn you about that. So here's the overall idea. We conceptually slice with a plane on a face of Q. So you have Q inside P, and take some face of Q and put a plane on it, and imagine slicing off and taking off this hunk of P that you've just cut off. But we're not actually going to do this cut. This is just conceptual. Then this piece that we removed, so to speak, we partition it into what we call generalized domes, or G domes. And then we partition those into pyramids. And then for each pyramid, we do diagon tailoring to reduce each pyramid to its base. And all these pyramids are kind of stacked on the surface with their apex accessible, and you do this process of snipping, and then it ends up that you've reduced the hunk of P that you've taken off to be the face of Q that you sliced. And then you do it for another face of Q, then you do it for another face of Q. And you keep doing this, and you get them all. So I'm now going to walk through each of these steps. So a dome, David Epstein calls them cretopes in higher dimensions. A dome is a polyhedron that has a distinguished face, the base, and all the other faces touch it. The usual definition of the dome is that all the other faces share at least an edge. We only needed that they share even a vertex. And so we call them generalized domes. So this is a dome. X1, X2, X3 is the base. I'll continue to use X for the base. And you can see that there are, that every other face touches the base. So now I'm going to have to ask you to imagine that Q is somewhere down at the bottom of this dodecahedron, and it has a face on which this plane lies. And this, when I said we were going to remove a hunk of P, it's everything up above. But first we partition it into domes, into these G domes. So you imagine taking this red or orange plane and rotating it up around that edge E, one edge of the face, so that it bangs into the polyhedron. And that is pi 0. And then keep rotating all the way down until you go to the other side. and stop if the piece that you got between the two adjacent planes is a G-dome, but if you go a little further, it ceases to be a G-dome. So it's not very easy to see there. But maybe, let's see. Well, I think it's just not very easy to see, but
What's the base in this case?
I'm not sure I know what you mean by base.
Well, it's
Oh,
the base of.
there's a
the-
face under here that you can't see,
Oh,
and this is one of the edges of it.
so you're saying G dome with respect, with that as the base?
Yes, so we're going to, this right here is a G dome, this is a G dome, this is a G dome, this is a G dome, and that's it. And it's fairly simple. You just keep going until the next step. You're going to make something that's not a G dome anymore because faces are no longer touching the base. Oh, I see what you meant by the base. I'm sorry, I didn't understand that. So the first base is X1, X2, B1.
I see.
Then the next base is X1, X2. I haven't labeled them.
Oh, I see. So
This
the
one-
base is,
So the planes keep on rotating, but the character changes.
Yes. And you stop because I want to get these pieces that I know how to handle, the G-domes. Actually, ultimately, I want pyramids, but we couldn't figure out a way to get directly to pyramids. So we have this intermediate step of the G-domes. I have another example. This is like an abstract example. I have a real example of the cube and the tetrahedron, which maybe this is clearer because it's so much simpler. So we want to imagine laying a plane around right on that base of Q and rotate it around P1, P3. And P is the cube surrounding it. And here you have P1, P3, P7, P5, that's a base. And this is a G dome. But if you went a little bit further, this would cease to be a G dome. So you stop there, and that's one G dome. And then you continue, and then we get P1, P3. P8 is the base. And this here, and now I pulled them out separately. So this is the first one, and this is the second. Maybe this is easiest to see. Take P1, P4, P7, P5, that's the rectangular base. And this, and the other faces, they all touch it. So that's a G dome. And here the base is P1, P3, P8, and P7 and P5 are above. So in this case, the portion of the cube that I'm going to remove, I've now partitioned into two G domes. And later we'll see that each of those two G domes is partitioned into two pyramids. So now,
G domes are Halen graphs, right?
yes,
Okay.
I didn't even know that terminology, yes.
You start with a tree, and then you put a circuit around through the leaves of the tree.
What did we call
Halen, Halin.
it? Right, and we're not using any of the properties of the Halen graph. But the base is the cycle,
Okay, right.
and the leaves, you have a tree, which is why David Epstein calls it a tree tool. Okay, so now I'm going to, this is one of the hard parts. How to partition a G dome into a pyramid, into pyramids. This is what a pyramid is, convex polygon, an apex that is not in the same plane. I'm going to use X for the base. So this is an example we worked out carefully of a G dome getting reduced to pyramids. And this is the start. So there's a base here and every face touches. And there's a tree up here, which happens to be just an edge. P1, P2. In general, there'll be a more complicated tree on top and you whittle away one vertex at a time. But here, what we'd like to do is take this and make it into this, which is then a pyramid over the same base. We don't want to destroy the base because we have to keep that fixed. And so we have a number of steps to accomplish this transformation. And as I said, this is one of the hard parts, so I'm not going to spend too much time on it, but at a very high level, we start here and make a cut that I'll explain in a second, and that leads to a different polyhedron, and then we pull off pyramid here, and then a pyramid here, and a pyramid here, and a pyramid here, and then we're into a new domain, and we keep doing this, and eventually we get the first picture I showed you. So let me give you at least a little hint of this. So we want to get rid of B1, which had all these edges here. So we take a plane lying on X1, X2, B2. And that undercuts D1 and produces this A3, A4, A5, A6, etc. And then, and A6 has 1 degree less. And now we start peeling off pyramids, this X2, X3, A4, we pull this off. And each time we have to slice with a plane that is on the boundary of the convex polygon base. So we don't want to destroy that. And this continues. Here I circled. We're kind of marching along the base, getting rid of these. Each time their little pyramids come off. And I know that's not convincing, but we end up reducing. That vertex is gone and it increases the degree of this. And then we keep doing that over and over again. And we'll get lots of pyramids, many of them small, and in the end we get one pyramid. So let me return to this example. Remember, we got 2 G domes, which are pretty clear here at the bottom. And this, unfortunately, is not clear, but if you apply what I was illustrating with those complicated examples here, this G dome, the first one gets partitioned into 2 pyramids, and the second one gets partitioned into 2 pyramids. So this is the G dome. X1, X2, X3, that's the base vertices and partitions into 2 pyramids. So in that case, with the cube and the tetrahedron in the corner, we get 2 G domes, each of them is 2 pyramids. And later I'll show you that they're stacked in a certain sense and that they're all accessible from the outside. Oh, here. Not later on, the next slide. So now, this is a pyramid whose apex is P2. So you can remove that. There's a pyramid whose apex is P6. Then P5, and finally P7. And once you remove this, you're back with the face of the cube. But what I mean by the pyramids are stacked is that I can now slice this off. And you'll see, I shouldn't use the term slice because we don't slice it. We're going to tailor down to it. But I need to be able to reach P2, then P6, then P5. And they're all accessible. They're not buried inside where you can't remove them. Let's see. Yes. Okay. So back to the algorithm. Now we have lots of pyramids. And for each pyramid, one at a time, we do diagon tailoring to flatten it to its base. Then we take the next pyramid and diagon tailor flatten to its base and continue until you end up with the face flat on the cube. And so I think I better just show the picture here because so here's a pyramid, and let's look at this for a minute. This angle is 70 degrees, but this is a regular hexagon, so there's 120 degrees on the base and 140 above it, so there's extra 20 degrees. And you have 6 angles of 40, 120 up there. So a curvature of 240 minus the 120. And what we're going to do is squash this by these tail lines. But we're going to, in order to like lay this gamma 1 edge down, you have to remove 20 degrees because it has 140 here, but it has to be 120 when it's flat. And this is a view of the whole process for that hexagon. Here is the gamma 1, which I've now opened up. So you can just cut down gamma 1 and lay it out so you can see what's going on. And then here is the first diagon from X1 up to this point, down to here, surrounding V. Let me go back so you see what V is. So V is the apex. So this is the first diagon. I'm going like this, around there, to a point on the back that you can't see. That's this point here. And I choose this so that there's a total of 20 degrees here because I have to reduce the 140 to 120. And then, of course, you suture closed. And I've removed V, but I've added this vertex here. And you do it again and again and again. And the very last step, you take a diagon that has two, both ends of the diagon are vertices. Whereas these have one end of vertex and you break a new one. So initially you have this, okay, let me go back to this. I can see this is, must be so confusing. So you have the 6 base vertices, they're going to remain. They're not going to touch those. But the first diagon surrounds V. So you get rid of V, but you add a vertex. Then the second diagon goes around that new one, etc. Each one based on X1, X2, X3, X4. One by one, removing the angle until it gets completely flattened, and then it looks like this. And one of the complexities here is these, we call these seals, because that's where you sealed with Alexandrov's theorem. They all flip one another, they intersect one another in a kind of complicated fashion. Okay, now here, there are 2 things we need to make this work. One is we have to be able to remove enough angle to flatten. And imagine that, like I got greedy and I wanted to take more angle out here. This would go deeper into the top of the pyramid. So you have to get the angle just right. And the new vertex that you create has to lie on the top and not on the base. Otherwise, it's not going to work. So they're very tricky things to accomplish here. And we use the star unfolding, the cut locus, as I mentioned earlier when you asked the question, to help us with this. This is just a picture on the cube. I think many of you have seen this before, and I'm not going to go too much in detail there. But this is maybe the hardest part of the proof. It kind of explains what I was trying to say. The proof of this part claims that the cut locus, each time you look at the cut locus, and we want it to remain entirely on the top of the pyramid and not on the base. Because if it lay on the base, we'd be cutting the base, but we only want to take the top of the pyramid and push it down and not damage the base, so to speak. So it has to not touch the base. And because the reason we need that is so that the base, which keeps changing each time in terms of its geometrical structure in a way that we don't know because we can't use it. We can't algorithmically use Alexandrov's gluing theorem, but we know it's pyramid-like. And it turns out that kind of a nice surprise that we use Cauchy's arm lemma here. And some of you have heard about it. I'm not going to explain it, but we use that in the proof. And then secondly, we need to have the diagonal angle at xi every time you're doing this cut here. You need to have this angle, which at this point in the proof is called alpha I plus 1, to be big enough so that you can flatten. And for that, we use the cut locus. And I'm not going to be able to explain this, but I did make a model of it. And this is a pyramid with a base, but this is the star unfolding from this point xi plus 1, this point. And so we don't really know it would look like a pyramid because we don't have the shape of it. And we don't know the shape of the thing in 3D, but we understand the surface completely. And here we use a nice lemma from Jinichi Ito and Costin Vilko in another paper that if the cut locus is a path, then you must have a doubly covered polygon. This is easy to see in one direction. If you take two convex polygons, if you make a doubly covered convex polygon and pick, let's say, one corner as the source of the cut locus, then of course you can go to a point on the top or the bottom. They're exactly the same length, and so every point around the rim is on the cut locus. So if you have a doubly covered polygon, the cut locus is a path, but it's if and only if. And we use that. So again, I'm not going to explain it. I'm just kind of saying this is part of the heart of the proof. Okay, so I think I've explained that as best I can. Yeah, and I mentioned the seals clip one another. You know, here they get glued, but then this purple one goes right through the part that was glued, and you kind of lose some of it. And we studied this a little bit to try to understand it, and I actually implemented this portion of the algorithm. And we could prove that the seals end up to be a tree. If you do the tail in the order that I was showing you for any pyramid, you get this nice pattern. And we don't quite know what to do with it, but anyhow.
When you say tree, what?
I mean, there's no cycles here. If
Oh,
you just look at the
of
red.
course. Okay. No problem.
Yeah, I'm sorry,
That's great. That's fine.
combinatorial tree. Okay, so I hope maybe you have a whole idea. So again, let me repeat, and this is the last time I'll repeat it. So we take each face of Q. Imagine putting a plane on it, doing this rotation of the plane to peel off, to turn the other part into a bunch of G-tones, which then we turn into a bunch of pyramids. And then for each pyramid, we do this walking around the edge, click, 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 and get it flat to its base. Then the next pyramid is accessible, and you do it again and again and again. And it all goes down to that one face of Q. And then you repeat for another face of Q. We didn't really work on the algorithm too much. It's all I cared about initially was that it be a finite algorithm, and then it'd be nice if it's a polynomial time algorithm, and it is. And I don't think I should walk you through this. It's not very interesting, because the biggest issue is what if we have to use Alexandrov's gluing theorem at every step? We're in trouble. Well, so the hard part was to avoid actually using, well, we're using his theorem to make sure that the thing is convex, but then all the computations are just done abstractly with a data structure that models the surface. So like you can find a cut locus. You don't need to actually have the three-dimensional shape to find the cut locus. So we rely on that, and it ends up to be about n to the fourth, and surely faster than that. Okay, so that's the end of the proof. Any questions on that, or shall I go on? Okay. So 2 corollaries and then 3 open problems. So again, if you have 2 convex polyhedra Q inside P, we can enlarge Q by insertions of surface so that it unfolds Q onto P from the inside. And the idea is kind of simple. First, tailor P to Q, but keep track of everything that you've done. You've cut out all these digons, and I've done this with paper, and they're just all over the floor and a mess. But here you have to keep track of everything you did, where you did it, and then start with Q and cut each sealed geodesic and reinsert the digon that you removed on your way down to Q. And you will inflate Q onto P with all of Q's surface remains, and a whole bunch of inserts from P are in there. And there's a lot we don't know about this, but it's in a sense, it's unfolding one convex polyhedron onto the inside of another. And we did this for a few small examples of doubly covered polygons. I think this is be very hard for me to actually do this. Even for the cube and the tetrahedron, it's not completely clear how to do this, but it would be quite interesting, I think. So that's one corollary. And here's another one that I like. For 2 convex polyhedra Q inside P, there exists a continuous folding of P onto Q. So what we mean here is no cutting. You just take the surface of P and you fold it, each fold being a continuous movement, and you squash it down on the Q's surface. And this, instead of, let's see, let me go to a picture made here. Suppose you have this diagon XY surrounding the vertex Z that you want to cut out. That's part of the process. Instead of cutting it out, what I want you to imagine doing is taking a teeny little diagon that just barely goes around Z, from X to just right beyond it on the cut locus coming out of Z. And to use Anna's example, pinch it in your fingers and then pull more of the paper slowly until you get the whole diagon, but don't cut it. We've now made a doubly covered triangle that sits on X, Z, Y. And then flop it over onto the surface. And then pretend that the surface gets melted into it. And then do it again and again and again. And you will slowly fold the surface, fold one surface onto another, rather than cut. And this, we don't have an algorithm for this. This process of pulling the doubly covered triangle out of the diagon very slowly needs to, in some ways, to apply Alexander's gluing theorem at every single instant. And I really have no idea how to handle that. So okay, so some open problems. The first one is to find a cut locus generic point, which Boris should remember. We did this a long time ago in our paper where we proved that there can be no more than n to the 4th cells where if you have the source point of the cut locus in that cell, it's generic. The shortest path to every vertex is unique. There's never another one. And not in the algorithm I showed you, but in other parts of our work, this is the bottleneck. And I don't know if it can be done in less than 10 to the fourth time. And we didn't really try. So, second problem, is there a finite algorithm that determines a continuous unfolding of P into Q? That's what I was just talking about. We don't have an algorithm. And it seems hard, but there's quite a bit of work on flattening polyhedra, flattening boxes, like maybe 10 papers on this. So I think this is an interesting new direction. Rather than flattening to the plane, we flatten onto another object. And this is almost like every time someone gives a talk and they say, well, what about higher dimensions? So as soon as you talk about convex polyhedra, you want to know, what about non-convex polyhedra? And Alexandrov's gluing theorem no longer applies, and it seems very difficult to make progress, but probably there is some way to do it, but for us, that's a complete mystery. All right. The end.